Rock-forming minerals. Rock-forming minerals are the essential components of the Earth's crust and play a critical role in determining the characteristics of rocks. These minerals form the building blocks of igneous, sedimentary, and metamorphic rocks and are among the most abundant and significant materials on Earth. Understanding rock-forming minerals is fundamental in geology, as it helps in identifying rocks, interpreting their formation processes, and studying the Earth's geological history. Characteristics of rock-forming minerals. Rock-forming minerals are usually stable under a wide range of temperature and pressure conditions, allowing them to form and persist in diverse geological environments. They are often classified based on their chemical composition and crystal structure. Most rock-forming minerals belong to a few major mineral groups, including silicates, carbonates, oxides, sulfates, and halides. Major groups of rock-forming minerals. 1. Silicate minerals. Silicate minerals are the most abundant group of rock-forming minerals, making up about 90% of the Earth's crust. They are composed of silicon and oxygen, often combined with other elements like aluminum, magnesium, iron, and potassium. Silicates are categorized into different subgroups based on the arrangement of their silica tetrahedra. Quartz, a simple silicate mineral made entirely of silicon and oxygen. It is a key component of many igneous and metamorphic rocks. Feldspars, these are the most common silicates, divided into two subgroups, alkali feldspars, e.g., orthoclase, and plagioclase feldspars. Feldspars are found in nearly all rock types. Micas, these minerals, such as biotite and muscovite, have a sheet-like structure and are common in igneous and metamorphic rocks. Olivine, a high-temperature silicate mineral found in mafic and ultramafic igneous rocks. Pyroxenes and amphiboles, these chain silicates are essential components of many igneous and metamorphic rocks. 2. Carbonate minerals. Carbonates are composed of carbon and oxygen in combination with calcium, magnesium, or other metals. Calcite, the most common carbonate mineral, forming sedimentary rocks like limestone and metamorphic rocks like marble. Dolomite, a key mineral in dolostone rocks. 3. Oxide minerals. Oxide minerals consist of oxygen combined with one or more metals. They are essential in various igneous and metamorphic rocks. Hematite and magnetite, common iron oxides found in many rock types. 4. Sulfate minerals. Sulfates contain sulfur and oxygen, often combined with calcium or other elements. Gypsum, a significant sulfate mineral in sedimentary rocks. 5. Halide minerals. Halides are composed of halogen elements like chlorine, fluorine, or bromine combined with other elements. Halite, commonly known as rock salt, it forms through the evaporation of saline water. Importance of rock-forming minerals. Rock identification. The composition and texture of rocks depend on the minerals they contain, making mineral identification crucial in geological studies. Economic significance. Many rock-forming minerals are sources of valuable metals and materials, such as feldspar for ceramics and quartz for glassmaking. Geological processes. Studying these minerals helps geologists understand the conditions under which rocks form, such as temperature, pressure, and chemical environment. Environmental indicators. Minerals like gypsum and halite can indicate past climatic conditions, such as arid environments or evaporative settings. Rock-forming minerals are not just static components of rocks, they actively participate in Earth's dynamic systems, including the rock cycle, plate tectonics, and weathering processes. Their study is foundational to geology, helping to unravel Earth's past and predict its future. Characteristics of rock-forming minerals. Rock-forming minerals exhibit a range of physical, chemical, and structural properties that make them unique and distinguishable. These characteristics are essential for identifying minerals in the field or laboratory and understanding the geological processes that shape the Earth's crust. Below is a detailed exploration of the key characteristics of rock-forming minerals. 1. Abundance in the Earth's crust. Rock-forming minerals are the most common and abundant minerals in the Earth's crust, forming over 99% of its volume. These minerals, primarily silicates, occur in various rock types, including igneous, sedimentary, and metamorphic rocks. They are fundamental in constructing the planet's lithosphere and significantly contribute to shaping landscapes and geological features. 2. Crystalline structure. Rock-forming minerals are crystalline, meaning their atoms are arranged in a repeating three-dimensional pattern. This regular arrangement gives rise to various crystal systems, such as cubic, hexagonal, tetragonal, and monoclinic systems. The crystal structure of a mineral determines its physical properties, such as hardness, cleavage, and fracture. For example, quartz has a hexagonal crystal system. Feldspars belong to the triclinic or monoclinic systems, depending on the subgroup. 3. Chemical composition. The chemical composition of rock-forming minerals is relatively stable and defines their identity. Most of these minerals consist of elements like silicon, oxygen, aluminum, magnesium, calcium, potassium, iron, and sodium. Silicate minerals contain silicon and oxygen as their primary building blocks, forming silica tetrahedra. Carbonate minerals feature a combination of carbon and oxygen, as seen in calcite. The chemical composition often determines the mineral's role in rock formation and its stability under specific geological conditions. 4. Physical properties. Rock-forming minerals exhibit a range of physical properties that make them identifiable. Hardness, measured on the Mohs scale, this property indicates a mineral's resistance to scratching. For example, quartz has a hardness of 7, while feldspar is around 6. Cleavage and fracture. Minerals break along planes of weakness, cleavage, or irregular surfaces, fracture. Mica has perfect cleavage, while quartz fractures conchoidally. Luster, the way a mineral reflects light. It can be metallic, vitreous, glassy, pearly, or dull. Color and streak. While the color of a mineral can vary due to impurities, the streak, color of its powdered form, is more consistent and reliable for identification. Density. Specific gravity minerals have varying densities depending on their composition. For instance, metallic minerals like magnetite have higher densities than silicates like quartz. 5. Stability under geological conditions. Rock-forming minerals are stable under specific temperature and pressure conditions, influencing their occurrence in different types of rocks. For example, quartz is highly stable and found in various rock types, from granite to sandstone. Olivine is stable at high temperatures and commonly found in mafic and ultramafic rocks but alters to other minerals at lower temperatures. The stability of minerals is also tied to their chemical composition and the environment in which they form. 6. Role in the rock cycle. Rock-forming minerals are dynamic and can transform under changing geological conditions through processes like weathering, metamorphism, and melting. For instance, feldspar in igneous rocks may weather into clay minerals in sedimentary rocks. Carbonates like calcite recrystallize under heat and pressure to form marble during metamorphism. 7. Optical properties. In thin sections under a polarizing microscope, rock-forming minerals exhibit unique optical properties that help geologists identify them. These include birefringence, interference colors, and pleochroism. Quartz shows no cleavage and low birefringence under polarized light. Biotite displays pleochroism, where its color changes when viewed from different angles. 8. Association with specific rock types. Rock-forming minerals often occur in predictable associations with specific rock types. Igneous rocks, dominated by silicate minerals such as feldspar, quartz, olivine, and pyroxene. Sedimentary rocks, composed of minerals like quartz, calcite, and clay minerals, often formed through weathering and deposition. Metamorphic rocks contain minerals like garnet, biotite, and amphibole that form under high pressure and temperature. 9. Economic importance. Many rock-forming minerals are economically significant, serving as raw materials for various industries. Quartz, used in glassmaking and electronics. Feldspar, a key ingredient in ceramics and glass. Calcite, mined for cement and lime production. Mica, used in insulation and cosmetics. 10. Durability and resistance. Certain rock-forming minerals, such as quartz, are highly durable and resistant to weathering, making them prominent in sedimentary environments. Others, like feldspar, are more prone to chemical alteration, contributing to the formation of secondary minerals like clay. In summary, the characteristics of rock-forming minerals reflect their chemical composition, physical properties, and geological roles. Their abundance, crystalline nature, and behavior under various conditions make them essential components in the study of Earth's materials and processes. Understanding these characteristics is fundamental for geologists to identify, classify, and interpret rocks, contributing to broader insights into the Earth's history and evolution.